an equation to predict the size of the force of gravity between two masses. So notice we need two masses, and they have some separation they're going to call r. So this force of gravity is equal to big G. This is called the universal gravitational constant. It's the same for every object, everywhere, not just on Earth. Then we multiply the masses together and divide by the space between them squared. Okay, so that's a formula hopefully we've seen before. So what it asks here is what's happening in terms of the forces. So you have the Earth is standing on, the Earth, and we have some astronaut is standing on the Earth. Draw a sketch of your friend in the Earth during the jump. Label the quantity r, draw a force diagram. Okay, so here's my astronaut. This is obviously not to scale, and he's jumping. So this distance between the center of each of their masses is called r. Now, the astronaut has a force, and it's going to pull him downwards towards the Earth. So he has a force coming from his middle downwards. The Earth has a force from the astronaut. My Earth is getting smaller. It's actually obviously much, much bigger than that. But the Earth has a force, I'll draw it from here, going upwards. So these forces are both going to be calculated exactly the same way. G, which is a constant, that distance between them is the same. Mass of Earth, mass of astronaut. Doesn't matter which one we put where. So these forces are equal. The only thing that's different is the direction. Okay, now it says calculate. Use this equation. So right here, use this equation and find an algebraic expression for the ratio of force per unit of mass of the astronaut. So I want you to find Fg. So go through this calculation. G is given right there. Mass 1 is going to be your astronaut. Mass 2 is going to be the Earth. And the radius is going to be right here, 6.3 times 10 to the 6 meters. Don't forget to square it. Then I want you to take whatever value you found and divide by the mass of the astronaut. And in this case, the mass of the astronaut, we said, was 100 kilograms. I want you to use correct units, and then you're going to find something kind of interesting. A number we've seen before is going to come out. So be careful with your units there. The big thing that I want you to come out of here is even though those forces are equal on both the Earth and the astronaut, force is equal to mass times acceleration. So I want you to think about the Earth. The mass is huge. I want you to think about the astronaut. Teeny tiny mass. So in order for these two things to be different, this acceleration needs to be teeny tiny, and this acceleration is really, really big. So even though we can't sense this force that's happening on the Earth, the reason is because its mass is so big and its acceleration is so small. The reason we can feel ourselves being accelerated to the Earth is our mass is so small compared to the Earth. Let's look how different they are. 100 kilograms versus 5.98 times 10 to the 24 kilograms. So just a smidgen in comparison. So we have a tiny mass, so we feel a larger acceleration. Okay, so that is the point of this assignment. If you have any further questions, don't be afraid to ask.